I think I mentioned this already, but I fixed the discrepancy between the assignment sheet and the Google Calendar, so everything should be good to go. As I mentioned, the second slide is the answers to day 10, so if, for those of you that weren't here Friday, you can go and look later and check your answers. All right, so big topic today, we're going to talk about continuity. On the surface, it's a very easy topic. There are a couple little things in there that, that make things a little bit more interesting, but for the most part, it's pretty straightforward. All right, we ready? How's everybody's weekend, by the way?
Good.
Good?
Good.
Huh?
How was yours?
Very nice. Thank you for asking. Jimmy?
I took the ACT and there was a limits question.
Yeah.
On the ACT?
Yeah.
They didn't
Wow.
phrase it like a
No, it wasn't
regular.
phrased like limit. It was, how do they say, like as X approaches.
Can you talk about this, or will the ACT come and kill you? Okay.
You don't repeat it.
It's like
Okay.
as
Yeah.
the x gets larger and larger towards positive infinity, what happened? Like what
So
does
like
the graph?
this,
Did
yeah.
you get it right?
I think so.
Oh, good.
Yeah.
Okay, so we'll talk about continuity and some open interval versus closed interval stuff. We'll look at one-side limits, which doesn't make any sense right now, but it will later. And we'll talk about the properties of continuity. That's easy. And then the big one is the intermediate value theorem. There is a rule in calculus. If a theorem has its own name, it's really important. It's going to stay with us for the longest. That doesn't mean you can forget all this other stuff, but in particular, IVT will be with us all the way to the end. Okay, so what does the word continuous mean? Simple question. Jimmy?
Doesn't stop.
Doesn't stop. Okay? Is that good? We all agree? Want to add anything to it? Will it change mathematically? If now I take that definition of the word continuous and I put it in a mathematical setting, do you think I have to tweak it at all, or is it good?
The formula wouldn't change, or the expression.
Pretty good there. We're going to talk about continuity of a graph, and we use a bunch of words. Continuous, continuity, discontinuous, non-continuous. All these other fun things will start showing up. Okay. Simplistic terms from a mathematical standpoint, can you draw this graph from point A to point B without picking up your pencil? Okay. We're going to get into a lot of weird calculus stuff. We'll talk about holes and jumps and gaps and removable discontinuity and infinite discontinuity and all this other garbage. But all it boils down to is really simple. Can I get from point A to point B without picking up my pencil? Are you with me? Good. So we're pretty much done with continuity. Now we just got to polish it up a little bit. Okay. So here's the formal definition of continuity. This is something, these three things pop up all the time. So the bottom thingamajabber, what is that? Paragraph is not that important. But 1, 2, and 3 is something you want to write in your notes. You want to put a box around it with stars and maybe some arrows pointing to it and highlight it so that you can find it easily. In order for a function to be continuous, you need to be able to satisfy all three of these conditions. And once you write them down, I'll explain them to you. Now I'll try to burn my mouth. Okay, number one is exactly what it says. There's got to be a value at the function. So what C means is we're going to look at some interval of a function. We're not going to talk about the whole function. We might, but we're going to just look at a chunk of a function from A to B. And then we randomly pick some point C between A and B. Doesn't matter where. Number one says no matter what C you pick, it has to be defined. It has to have a value there. Part 2 says no matter what C you pick, there has to be a limit there. And then part 3, which is the most important part, the value from part 1 and the value from part 2 have to be the same amount. And instead of talking about continuity and understanding continuity, it's easier to look at discontinuity to explain continuity. So what's going to cause problems? There's 3 things that cause problems with continuity. Okay, which creates what's called a discontinuity, or a spot where it's non-continuous. Are you good with this? Yeah. Okay, good. Here's the first one. It's called a removable discontinuity. You would know it as a hole. But the fancy calculus term is a removable discontinuity. If you go back to the simple definition that I had on one of the early slides, you can see I can't go from this point to this point without picking up my pencil because there's a hole there. Okay. So that creates a discontinuity. I'm not really sure what the AP board is going to look for on the test. If they ask you for the type of discontinuity, I don't know if they would accept hole as an answer. I think you would have to use the term removable discontinuity, so you got to know that term. We've talked quite a bit about holes in graphs, so I don't know if we need to spend more time on it. Does everybody understand this first one? Okay, good. What do you think a jump discontinuity would look like? Where have we seen those?
You've done enough today.
Raj, what do you got?
It's a hole, but it's filled in with at the spot.
Good. Where have we seen that? Yeah, piecewise functions. Okay. Jump discontinuity. Okay. Piecewise function. Good. There's a hole, but it's filled in with a different value. Or there's a jump. And I think it's obvious that I can't draw that red stuff without picking up my pencil. And the last one, infinite discontinuity. Sid, what do you think that is?
There's a lot of, as many holes?
No.
No?
No, because if you had an infinite number of holes, that would be nothing.
Okay, true.
Yeah. You'd have just a blank graph. Anybody else? What's an infinite discontinuity? No, we heard from you already. Somebody else. Michael.
That function.
That would no. That would actually be a jump discontinuity. Okay. Here. Asymptote, correct. Infinite discontinuity goes on forever, going up to positive infinity or down to negative infinity, generated by an asymptote. That's it. No matter what else pops up in a function that's going to cause problems, they can be explained by one of those three things: removable, jump, and infinite. And sometimes you can get crazy and have more than one in the same graph. Once you have one thing, you're done, and it's discontinuous. Okay. Let's look at this function. F of x is equal to the square root of 4 minus x squared. Dante, what can you tell me about that function? What's it look like? What is it? How big is it? Doesn't have a hole, correct? Good start. Alex, what's it look like? Nope. Good guess though. Because you saw square root function, you figure it looks like the square root function.
It's the other way because that's negative.
Nope. Maggie.
Isn't it a semicircle?
It is a semicircle. Top, bottom, left, or right? Top, bottom, left, or right? The top, very good. What's the radius of that semicircle? 2, and where is it located?
The center, what do you call that?
That's the center, yeah.
It's on the origin.
Good.
Yeah, thank you.
Okay. So I got a picture of it in here somewhere. There it is. Okay. Now, is that function continuous on the interval from -2 to 2? Yeah. Because I can go from -2 and get to 2 along the function without picking up my pencil. Now, what about -2? We start talking about something called a one-sided limit, and this is a fairly easy concept. And I think you'll all agree with me. As I approach -2 from the right-hand side, is it obvious that the answer is 0? Anybody have a problem with that? Okay, come along here, and when I get closer and closer to -2, I get closer and closer to 0. It's pretty much a plug and chug problem. What if I come from the left-hand side? What if I start over here? What's the limit? Or I should ask, what problem occurs? There's nothing over there, right? So what do we do with the limit? Well, it appears that it's going to be 0, but I have nothing over here. And so the way we handle one-sided limits is we don't. So if you have a function where there's nothing on one of the sides, you can't have a limit when there's no part of the function. So that breaks down. And we've done this already, but this is another way to test for a limit, and it's another way of also repeating the idea that we've covered already, which is the left-hand limit has to match the right-hand limit. Jimmy.
So that limit undefined then?
That limit is undefined, yes. There's a right-hand limit, there's no left-hand limit, and there's no limit at the point. So that, you knew that already. There's the fancy definition for a closed interval, which we don't really care about. Let's skip on the properties. You know what? Hold on. I want to go back. I forgot to talk about one thing. Let's go back to our discontinuities. Dun, 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 dun. Okay. So remember, there's three things for in order for a function to be continuous, there's three things that have to be met. It has to be defined. It has to have a limit. The limit and the definition or the value have to match. Which one does this violate? Or which of them does this violate? Is it defined at 1? No, done, not continuous. Does it have a limit at 1? Yeah, the limit at 1 is 2. And since 1 is screwed up, then 1 and 2 can't be equal. So this actually violates 2 of them. What about a jump discontinuity? Is it defined everywhere?
Yeah.
Yep. No matter where on that graph, it has a definition. Yes, there is a hole, but notice that the hole is still defined because it's filled in. Does it have a limit everywhere? No, there is no limit at -2. Why is there no limit at -2?
Left-hand limit doesn't.
Good, left-hand limit doesn't match right-hand limit. Coming from the right-hand side, I approach -1. Coming from the left-hand side, I approach 2. Okay. And then obviously 3 doesn't work because if 1 is a value and 2 has no value, they can't be equal. All right, what about an infinite discontinuity? Is it defined everywhere? No, that's screwed up. Does it have a limit? No, which pretty much none of them work here, so this is just a train wreck. Good. All right, so I just want to make sure you understood what causes the problems for continuity. And, okay. Properties are and I don't even know if you need to write this down, but this is just a continuation of something what we did with limits, which means that if you take two continuous functions, you add them, it'll be continuous. If you take two continuous functions and you subtract them, they'll be continuous. If you multiply two continuous functions, it'll be continuous. If you divide it, it'll be continuous. You know, pretty much no matter what you do with two continuous functions, they're going to stay continuous. Now there's one big thing that's coming up that people forget about. This is pretty straightforward, it's not a big deal. However, when we get to this, you need to remember this. All polynomials are continuous. X to the 6th minus 4x to the 5th plus 3x, blah, 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 continuous because it's a polynomial. But I assumed one big thing in that statement, that you all know what polynomials are. Is that a safe assumption? Is 2x minus 5 over x minus 3 a polynomial? No, it's a rational function. Okay, polynomials are the simple bunch of terms added up with exponents in them. Because you will be asked, why is this function continuous? And it's going to almost always happen that the reason it's continuous is because it's a polynomial. In fact, you'll need to check that in some of the examples. Okay, that might be something else you want to put a box around because it's really important. This is just a continuation of properties. So we talked about add, subtract, multiply, divide. Composite functions also work the same way. You take a continuous function, you put it into a continuous function, it generates another continuous function. Hot diggity. All right. Let's talk about the tangent. And everybody loves the trig. Is the trig function continuous? Patrick, is the tangent function continuous?
No,
Why?
because it has the asymptote.
Perfect. Good. It is not a continuous function. And when I say that, I'm referring to the interval from negative infinity to infinity. Suppose we take a smaller interval. Is the tangent function continuous from 0 to pi over 4? Yes. Good. Is it continuous from 0 to pi? No, correct. Okay, so anywhere there's an asymptote, it's going to create some problem. So in this problem, it says, describe the intervals for which each function is continuous. So I want to know where is the tangent continuous. You can do it one of two ways. You can actually cheat, and instead of saying where it's continuous, we can also say where it's discontinuous. So Patrick, remembering the tangent function, where do the asymptotes fall?
That pi over 2, 3 pi over 2.
Good. So pi over 2, and then it repeats every pi ad nauseum, right? Are you familiar with the term ad nauseum? It's Latin for until you puke. Okay, so it just continues in both directions. How do I express that? Anybody else? How do I express the, if we know that the first asymptote is at pi over 2, and it repeats every pi interval, how do I express that? That's it.
Plus 2 pi k.
Yep. Not 2 pi, just pi, it's tangent, yeah. So what I did here is I cheated. Instead of talking about where it is continuous, I talked about where it isn't continuous. It's not continuous on all of these guys. So even if you've got a function like the tangent that's a train wreck every pi interval, you can still talk about chunks of that graph that are continuous. Great.
So then, how would we put that in the interval?
You wouldn't. You can't. I mean, you can, but it would take forever.
When you write something like that, do you have to specify that n is an integer?
No, it's assumed. It's just there to show off. And I think you crazy kids today use k instead of n, right? Yeah, I went old school. I learned n, so I use n whenever possible. So there's the picture. And we talked about first, was it continuous from 0 to pi over 2, or pi over 4? Yes. Is it continuous between negative pi over 2 and pi over 2? Yes. But where does it start to create problems? Anywhere these asymptotes show up. And Patrick nailed it there. First one's at pi over 2, and then we jump an interval of pi every time. Okay. Now, this is a big deal, IVT. It's a simple concept. So, before you write this down, let me explain it to you. Let's suppose I've got a point here at 1, and I've got a point here at 5. You with me? If the function is continuous, I can't get from 1 to 5 without passing through 3. Does that make sense? Okay, that's it. That's the intermediate value theorem. It simply says if the function is continuous, and you go from one point to another, you have to pass all the other points in between. Now, here's the fancy calculus speak, though. It's continuous on the closed interval a to b, where f of a does not equal f of b, and k is any number between f of a and f of b. Then there is at least one number c in a to b such that f of c equals k. That always made me nervous the way they wrote that, but it's there.
Can you say it without watching?
Which one, that or the English?
The English.
If I go from one point to another and it's continuous, I have to pass all the points in between. Okay. And I've got an example that might help to clarify. This has some big applications for us. And if you understand the concept, the applications become pretty easy. There is a couple twists in there that we have to make sure that we get under control. Oh, we're doing fine for time. Okay, so again, if you're writing down this fancy schmancy calculus definition, that's great. I'm not going to tell you not to. But if it doesn't make any sense to you, don't write something down that doesn't make any sense. Okay. Paraphrase it, change it, whatever you need to do to make sense to you. They're your notes. Can I go or should I wait? That's okay? Wait a second? Okay. Now we're good? I'm going. All right. Simple explanation. Suppose a girl is 5 feet tall on her 13th birthday and 5'7" on her 14th birthday. First of all, that's not healthy to grow 7 inches in a year. Her knees are probably destroyed, but we'll ignore that. This should make sense that sometime during her 13th year, she must have been every height between 5 foot and 5'7". Does that make sense? So some days she was 5'1", another day she was 5'2", another day she was she didn't go from 5'2" and all of a sudden instantaneously end up at 5'5". She had to cover all those other heights along the way. The same thing is true with age. You know, you're not going to go from 18 to 19 without covering 18 years, 7 weeks, 3 days, 2 hours, 4 minutes, etc. Pregunta.
Does that mean that she went through an infinite amount of heights?
Correct. Yes. Theoretically. Right. Yeah, I mean, she, you know, it's not. She's bigger.
Yeah.
Yeah, there's no magic involved here. This isn't Harry Potter. This sums up the intermediate value theorem. Now, when we translate it to math, instead of talking about heights, we still talk about locations and going from one point to another point. If it's, and that's a key, that it's got to be continuous. If it's not continuous, you can just jump over the other value. But with it being continuous, it's got to hit all the values in between. Okay, and we're talking values as y values, not necessarily x values. Okay. All right. The way we use intermediate value theorem most frequently is we use it to find zeros of functions. Okay. Number one, are there zeros to a function? Number two, where are they? Initially, we're going to use intermediate value theorem just to justify the fact that there's got to be a zero in there. And you understand what I mean by a zero, right? Where the function crosses the x-axis. Okay. So what does that look like? It's really easy. So let's take this function. We got a cubic. I have a general idea of what that cubic looks like, but I don't, the 2x and the -1 kind of screws me up a little bit. So what it looks like is irrelevant. The question is, does it cross the x-axis between 0 and 1? Is there a 0 between 0 and 1? I can use the intermediate value theorem to solve this. However, I need to check one thing, and this is the most common mistake with IVT, is people forget the first part of the theorem. The first part of the theorem said, if it's continuous. So I need to explain, justify, or show that this function is continuous. Is it?
Yes.
Why?
It's a polynomial.
Bingo. Done. It's a polynomial. It must be continuous. That takes care of the first part. It's a polynomial. Second part. I need to know where it starts. Where does it start? And or how do I find out where it starts? And remember, we're talking about an interval here. I know the whole function starts at -infinity and ends at positive infinity, but I'm talking only about from 0 to 1. Correct? Beautiful. Plug in 0. What do you get? -1. Now I need to know where it ends. How do I figure out where it ends? Plug in 1. What happens when I plug in 1? 1 plus 2 is 3 is 2. So what happened there? I started at -1. I ended at 2. What does that tell you that the function must do somewhere in between -1 and 2? It's equal to 0. Okay, so plug in 0 like Greg said, we get -1. Plug in 1, we get 2. The intermediate value theorem says since the function is continuous, if I start down below the x-axis and I end above the x-axis, I've got to cross the x-axis somewhere along the way. It doesn't say where it crosses, it just says it crosses the x-axis. That's a different problem. Here we're doing is just, like it says, we're just showing that it has a 0. And again, fancy way of saying it goes from negative to positive. Okay, so you'll use zeros by looking for what's called sign changes. It goes from negative to positive or from positive to negative. All right, now suppose we complicate the problem. Suppose I want to know where that 0 is. How do I find it?
I'll plug in 0 if plug in the function equals 0.
What?
Set y equals 0.
There you go, set y equal to 0 and solve the function, which is a little tricky to do, but it's not what I asked you. Okay, so there's the picture. It crosses at that point C, somewhere between -1 and 1. Okay, so that confirms what we already knew. And that's how intermediate value theorem is applied. Like I said, the intermediate value theorem justifies that there is a 0 in that interval. It doesn't necessarily tell you where that 0 is. You may have to go find that on your own. Okay. We're all done. Okay, questions? Don't make this more complicated than it is. The only thing that should really be a little tricky for you is the 3 parts that cause problems. Is it defined? Does it have a limit? Do those 2 values match? Everything else should be pretty straightforward. Try to use the simplistic English